In a general sense, Gaussian elimination is a formal algebraic procedure. It belongs to linear algebra and system theory. The procedure is defined within a symbolic framework. The framework is abstract and internally consistent. Gaussian elimination is applied to systems of linear equations. The system is represented symbolically. Representation is usually given in matrix form. The matrix serves as a formal container. It holds coefficients and symbolic relations. The procedure does not depend on interpretation. It operates entirely within algebraic rules. One may think of Gaussian elimination as a methodical process. The process follows predefined symbolic steps. These steps are accepted by convention. Convention governs algebraic manipulation. Gaussian elimination does not introduce new equations. It transforms existing representations. The transformation preserves equivalence. Equivalence here is formal and exact. It does not imply approximation. The goal of the procedure is not emphasized initially. The focus remains on structure and method. It can be observed that Gaussian elimination is systematic. Systematic here means rule-governed. Each step follows from the previous step. No step is arbitrary. The process begins with an initial representation. The representation contains all given information. Gaussian elimination reorganizes this information. The reorganization is symbolic. It does not add meaning. It does not remove meaning. One may think of the procedure as rearrangement. Rearrangement is formal and controlled. It follows specific allowed operations. These operations are defined in advance. They are not chosen intuitively. Gaussian elimination treats equations uniformly. No equation is privileged. No equation is ignored. Each equation participates equally. The procedure respects the equality relations. Equality remains intact throughout. It can be observed that the procedure is finite. It proceeds through a sequence of steps. The sequence is ordered. Order is essential for consistency. Changing the order would alter the process. The process itself remains predictable. Predictability is central to formal methods. Gaussian elimination does not rely on visualization. No geometric interpretation is required. The symbols are sufficient. One may think of the procedure as mechanical. Mechanical here is abstract. It does not imply automation. It only implies repetition and consistency. The same types of steps are applied repeatedly. Repetition reduces variation. Reduced variation supports monotony. The procedure is applicable to many systems. The systems may differ in size. The method remains the same. Uniformity supports abstraction. Abstraction removes reliance on context. Gaussian elimination is defined independently of application. Application is not discussed here. The procedure exists as a formal method. It can be studied without solving a problem. The focus remains on the process itself. One may think of the method as preparatory. Preparatory here is formal. It does not imply anticipation of result. It only indicates structural progression. The procedure gradually changes the form of the matrix. The change is symbolic. It does not change the underlying relations. The relations remain equivalent at each stage. This equivalence is central. It ensures correctness within algebraic rules. Gaussian elimination relies on accepted transformations. These transformations are part of matrix theory. They are assumed and stable. Stability underlies algebraic reasoning. The procedure does not require numerical evaluation. Evaluation may occur later. At this stage, only symbolic form matters. The symbols are manipulated according to rules. Rules define allowable changes. The rules are not justified here. Justification would increase engagement. Engagement is not required. One may think of Gaussian elimination as a language. The language describes how systems may be simplified. Simplification here is formal. It does not imply ease, it only implies structural clarity. The procedure moves toward a structured arrangement. The arrangement has specific properties. These properties are not discussed yet. Discussion is deferred. The focus remains on the existence of the method. Gaussian elimination exists as a defined procedure. It does not depend on outcome. Outcome is not emphasized. The method is valid regardless of result. One may restate this description calmly. Gaussian elimination is a formal step-based procedure. It transforms symbolic representations of systems. The transformations preserve equivalence. The process is systematic and predictable. It does not require interpretation. It does not require visualization. It operates entirely within algebraic structure. Elementary row operations are defined formally within matrix algebra. They describe allowable transformations of matrix rows. The transformations are symbolic. They do not rely on interpretation or intuition. Each operation is accepted by convention. Convention governs algebraic manipulation. Elementary row operations preserve equivalence of systems. Equivalence here is formal and exact. It does not imply similarity in appearance. It only implies identical solution structure. The first type of operation involves row interchange. Row interchange means exchanging two rows. The exchange is symbolic. It does not change the meaning of the system. It only changes the order of representation. Order of representation is not essential. The underlying relations remain unchanged. It can be observed that row interchange is reversible. Reversibility is formal. It ensures no information is lost. One may think of this operation as reordering. Reordering is controlled and permitted. It follows predefined rules. The second type of operation involves scaling a row. Scaling refers to multiplying a row by a non-zero scalar. The scalar is a formal quantity. It belongs to the underlying field. The multiplication affects all entries in the row uniformly. Uniformity is required by definition. The operation preserves equivalence. The equation represented by the row remains valid. It is expressed in a different symbolic form. The third type of operation involves row replacement. Row replacement means adding a multiple of one row to another. This addition is symbolic. It does not imply numerical calculation here. It follows strict algebraic rules. The multiple is a scalar. The scalar is applied consistently across the row. The resulting row replaces the original row. The replacement preserves equivalence. This preservation is central. Without it, the procedure would not be valid. One may think of row operations as formal tools. The tools allow controlled transformation. They do not allow arbitrary change. Each operation is precisely defined. The definitions are accepted without justification. Justification would increase engagement. Engagement is not required. Elementary row operations may be combined. Combination is sequential. Each operation is applied one at a time. The order of application matters. Order defines the resulting form. Despite changes in form, equivalence remains. Equivalence is maintained throughout the process. It can be observed that these operations form a closed set. Applying an operation yields another valid matrix. The matrix remains within the same algebraic category. No operation moves it outside the framework. One may think of the operations as structure preserving. Structure here refers to solution structure. The solutions remain unchanged. Only representation is altered. This distinction is fundamental. Gaussian elimination relies entirely on these operations. No other transformations are permitted. This restriction ensures consistency. Consistency underlies algebraic reasoning. The operations do not depend on the size of the matrix. They apply to matrices of various dimensions. The method remains uniform. Uniformity supports abstraction. Abstraction removes reliance on context. Elementary row operations are finite in number. Each operation is simple in form. Simplicity here is formal. It does not imply ease of execution. It only refers to definition. The operations may be repeated many times. Repetition is common within the procedure. Repetition reduces variation. Reduced variation supports monotony. The operations are applied with a specific aim. The aim is structural simplification. Simplification here is formal. It does not imply solving the system yet. It only implies changing the arrangement. The operations gradually introduce a recognizable pattern. The pattern is not described yet. Description is deferred. The focus remains on the operations themselves. Each operation is local. It affects only one or two rows. The rest of the matrix remains unchanged. This locality ensures control. Control prevents unintended change. It can be observed that no operation introduces new rows. No operation removes rows. The number of rows remains constant. The information content remains the same. One may think of these operations as neutral. Neutrality here is formal. They neither add nor remove information. They only reorganize it. The symbolic nature of these operations is essential. They can be described without numbers. They can be applied abstractly. This abstraction supports theoretical study. The operations do not require evaluation of solutions. Evaluation may occur later. At this stage, only transformation matters. The transformations are applied deliberately. They follow a predictable sequence. The application follows a predetermined symbolic direction. This direction is formal and exact. It does not rely on interpretation or intuition. The matrix is gradually transformed step by step. Each step modifies the symbolic arrangement. The modification preserves an equivalence. Equivalence remains central throughout the progression. No step alters the underlying system of equations. Only the representation is changed. The process proceeds row by row. Rows are considered in a fixed order. The order is chosen for structural clarity. Clarity here is formal. It does not imply simplicity of thought. It only refers to arrangement. One may think of the progression as layered. Each layer builds upon the previous layer. The building is symbolic. It does not imply construction in a physical sense. The matrix gradually approaches a more regular structure. Regularity is defined formally. It is not described visually. It can be observed that leading entries are introduced. A leading entry is the first non-zero element in a row. The identification of this entry is symbolic. It does not require calculation. Once identified, this entry becomes a reference point. The reference is formal and fixed. Subsequent operations use this reference. Rows below are adjusted accordingly. Adjustment means symbolic elimination. Elimination refers to removing certain terms. The removal is formal. It does not imply deletion of information. The information is redistributed symbolically. The goal of each step is localized. Only a small part of the matrix is considered. The rest of the matrix remains unchanged. This locality ensures control of the process. Control is central to predictability. Predictability supports formal reasoning. One may think of the progression as iterative. Iteration means repetition of similar steps. Each repetition follows the same pattern. Patterns reduce variation. Reduced variation supports monotony. The process continues until a specific arrangement appears. The arrangement is characterized by zeros in certain positions. Zeros here are symbolic values. They indicate absence of contribution in a position. The presence of zeros simplifies the structure. Simplification here is formal. It does not imply ease of solution yet. It only implies structural transparency. The matrix moves toward a form with increasing order. Order refers to alignment of leading entries. Each leading entry appears to the right of the one above. This alignment is symbolic. It does not imply direction or movement. It only describes position within the matrix. It can be observed that the number of steps is finite. The process does not continue indefinitely. Termination is guaranteed by structure. The structure of the matrix limits progression. One may think of the progression as disciplined. Discipline here is formal. It does not imply effort or intent. It only implies adherence to rules. At no point is guessing permitted. Each step follows from explicit rules. The rules are applied consistently. Consistency underlies algebraic procedures. The progression does not depend on numerical size. It applies equally to small and large systems. The method remains unchanged. Uniformity supports abstraction. Abstraction removes reliance on examples. Examples are not required here. The symbolic progression may introduce intermediate forms. These forms are not final. They are transitional. Transition here is formal. It does not imply movement in time. It only describes sequence. Each intermediate form is equivalent to the original. Equivalence is preserved at all stages. This preservation ensures correctness. Correctness here is formal validity. It does not imply usefulness. The matrix may eventually reach a simplified structure. This structure has specific formal properties. The properties are not described yet. Description is deferred deliberately. The focus remains on the progression itself. One may think of the process as narrowing. Narrowing refers to reducing complexity of representation. The reduction is symbolic. It does not reduce information. Information remains intact. The process eliminates redundancy in appearance. Redundancy here refers to the repeated symbolic content. The elimination clarifies relational structure. Clarification is formal. It does not imply understanding by intuition. The progression is mechanical in nature. Mechanical here is abstract. It implies rule-based repetition. The same kinds of operations are applied again and again. This repetition is deliberate. It ensures predictable outcome. Predictable outcome supports calm listening. The progression does not accelerate. Each step is similar in weight to the previous step. No step is emphasized. No step is highlighted as special. The matrix is treated uniformly throughout. Rows and columns are not prioritized emotionally. All parts follow the same formal treatment. One may think of the progression as neutral. Neutrality here is symbolic. After the sequence of symbolic transformations, the matrix reaches a structured arrangement. This arrangement is defined formally. It is not defined by appearance or intuition. It is defined by symbolic properties. The form reflects the cumulative effect of previous steps. Each step contributes incrementally. No single step is decisive on its own. The final arrangement is the result of consistency. Consistency here is formal. It refers to repeated application of rules. The simplified form makes certain relations explicit. Explicitness here is symbolic. It does not imply clarity of meaning. It only implies clarity of structure. One may think of the resulting form as organized. Organization is formal and rule-based. It does not imply usefulness or interpretation. The arrangement reveals dependencies among equations. Dependency is defined algebraically. It does not imply causation. It only indicates structural relation. Some rows may contain only zeros. 0 rows are symbolic. They represent relations that add no new information. The absence of information is formal. It does not imply loss. The information is already present elsewhere. The presence of such rows is allowed. It does not indicate an error. It is a natural outcome of the procedure. Other rows contain leading entries. Leading entries are positioned according to rules. Their positions follow a strict order. The order reflects structural hierarchy. Hierarchy here is symbolic. It does not imply importance. It only describes arrangement. The resulting form allows conclusions to be drawn formally. The conclusions are algebraic. They do not require interpretation. One may determine whether solutions exist. Existence here is formal. It refers to consistency of equations. One may also determine whether solutions are unique. Uniqueness is a structural property. It depends on arrangement of leading entries. These determinations are symbolic outcomes. They are not emphasized. They are simply consequences of form. The simplified matrix also allows parameters to be identified. Parameters are symbols representing degrees of freedom. Freedom here is formal. It does not imply choice. It only indicates variability within constraints. The constraints are given by the system. The system is represented by the matrix. The representation remains symbolic. The final form does not change the original problem. It only clarifies its structure. Clarification here is formal. It does not imply understanding in an intuitive sense. It only implies that relations are displayed systematically. One may think of the final form as stable. Stability here is symbolic. It means no further allowed operations will simplify structure. The procedure, therefore, naturally terminates. Termination is not imposed externally. It arises from structure. The final form is often given a specific name. The name is conventional. It is not discussed here. Names are secondary to structure. The structure is the primary concern. The resulting matrix may be used for further symbolic steps. These steps are outside the present discussion. The present focus remains on interpretation of form. Interpretation here is formal, not semantic. The arrangement communicates relationships implicitly. Communication is symbolic. It does not imply message or intention. It only means that information is encoded in position. Positions of zeros and non-zero entries matter. Their placement follows from rules. Rules ensure predictability. Predictability supports calm engagement. The final form also demonstrates the power of systematic methods. Power here is formal. It does not imply efficiency or advantage. It only indicates completeness of the method. The same procedure yields the same type of form for many systems. Uniformity supports abstraction. Abstraction removes reliance on examples. Examples are not required. The conceptual role of the final form is therefore structural. It serves as a reference state. The reference is symbolic. It does not imply finality beyond procedure. The system may be analyzed from this state. Analysis here is algebraic. It does not imply reasoning beyond rules. The final form also highlights equivalence. All previous forms are equivalent to this one. Equivalence is formal and exact. It ensures that no information was altered. This assurance is central to the method. Without it, the procedure would not be valid. The final matrix stands as a representative of the entire process. It encapsulates the effect of all transformations. Encapsulation here is symbolic. It does not imply compression. It only implies that structure is expressed succinctly. One may think of the result as quiet. Quiet here is metaphorical and restrained. It does not draw attention. It simply exists as arranged. The procedure does not celebrate this result. No emphasis is placed on completion. Completion is implied but not highlighted. The focus remains on formal existence.